This week we're going to continue with our um, grain size analysis labs and look at the mechanical sieve. And remember last week we started this kind of series of analysis with the wet sieve process. Um, this week we're working on the dry sieve or the mechanical sieve, where we're going to get a much more finer resolution as we separate out the particle sizes from an original soil sample. Remember last week in the wet sieve, all we were able to do was separate out soil right here, right there along the 200 pan. So we were essentially separating out coarse soil, sands, and potentially gravels from fine soils, silts and clays. Sieves are essentially screens. If you've done any panning for garnets or gold or agates, you're familiar with sieve pans, and we order them in a descending size here, top to bottom, and then place a pan at the bottom to catch whatever is still able to pass through the smallest sieve size that we're going to be using in our analysis. And sieves are identified two ways. One in direct millimeters, the particle size opening in millimeters, or also, like up here in this upper row, um, sieve numbers. And essentially, we don't work with gravels too much in this class, the 3-inch or the half-inch even. We pretty much start here at the number 4 sieve. And what these numerical sieve numbers refer to is the number of openings per linear inch, not per square inch. And that's a real big mistake people make, especially on an exam. That's an easy test question I'm going to throw at you on the midterm here in a couple weeks. So we're primarily concerned with that range from a number 4 sieve through some intermediates to separate out our particle at a finer resolution down to that number 200 sieve. That's the finest um, dry sieve we have for our stacks. And just an example of kind of what this analysis can do for you visually. This is a soil analysis I did a few months ago, and I know I was talking about it in a different class. I can't remember if we looked at these pictures in this class. But this is a soil test pit 8 foot deep, and we're looking at the horizons here, trying to identify the different soil textures and the depths of those textures. So I've got 4 identified here that I took little bag samples of. And you can kind of see this first 10 inches is kind of a loamy topsoil. I saw a different texture here in the next 20 inches, 10 to 30. There's a kind of intermediate kind of a accumulation B horizon of clay down there. And then below that, I think this is our bucket number 7 that we're working with in our lab here. It's that pure silt. So what I'm looking at here, what I was interested in, was this second layer, this kind of B1 horizon, that 10 to 30 inches. And you can see it's this bag here. And this is what it looks like coming out of the ground. So it's an original soil sample. It's got air constituents, it's got moisture, and it's got the soil particles. And a mechanical sieve is done on a dry soil sample. So once this soil sample is dried out, I was curious as to what the individual makeup was on the different sieve sizes. And this is what it looks like after you run it through screens on kind of the predominant or the major sieve pans. I think I had a number 4, number 10, probably a 20 it looks like, 20 sieve. And then we're getting down into maybe 100 and a 200 sieve. And then this material right here represents what would pass a number 200 sieve. Or this material right here would represent the fines in that particular horizon of soil. Not nearly as much as I thought it would be. So ultimately what we're going to try and do with a mechanical sieve analysis is fill out a grain size distribution graph, or a gradation chart they're called. And they're charts that organize um, your sieve sizes, and the particular chart that I use is this one in this class, and I have copies of this in your lab manual. I'm also going to have copies of some of these next couple forms you're going to see. I'm going to have them posted on Moodle for you to print some hard copies to have for your resources. But on this particular um, distribution graph, they organize the sieves in descending size from left to right. So we have our larger sieve size. On the bottom here, it's grain size in millimeters. So 100 millimeters all the way down to 0.001, a thousandth of a millimeter. Then on the top, they have the corresponding size, both in inches and also sieve numbers. Um, The left-hand axis is the percent passing. These are percent passing by mass, and that's primarily what we're concerned with in this class this semester. And on the right-hand axis, it's percent retained. We're going to use that just a little bit, but this is more important next fall when we do some gravel gradations, when we're determining concrete mix design, proportioning out the number of pounds of gravel based on its gradation properties for a particular strength concrete that we're going to recipe up a batch for. Okay, and these are examples of what the results of a grain size analysis, or a dry sieve analysis, are going to show. We're going to have some sort of graph produced on that distribution graph. And the two I'm primarily concerned with here is this uniform graph, which is this kind of tall, skinny chart or line, and or the well-graded sample, which is this kind of broad or gradual. And what that means is what's the distribution of varying particle sizes making up your original soil sample, right? Uniform means you don't have very many different particle sizes. Just think of people in a uniform, right? Everybody looks the same. Same thing in the soil. If you have a uniform soil, most of your soil sample is made up of the same size particle sizes, as opposed to a well-graded sample where you have particle sizes ranging from large gravels, 1 3/4 inches, all the way down. We have representation all the way down here to your fines, right? We're down into our silts here of, looks like 5/1000ths of a millimeter. So we have representations all across that spectrum. What you notice in this uniform sample is that right, our left axis represents percent passing, or percent smaller, or percent finer, by weight or by mass. And 100% passing means 100% of your soil sample is going to go through that top sieve, or that sieve. And here we've got 100% of our soil sample passing a number 6 sieve, and no percent of our soil passing a number 40 sieve. So all of our soil in that sample is contained in a very narrow range of particle sizes, right? A number 6 to a number 40. That's basically pure sand right there. So what we're going to be curious to look at here with our 12 buckets of soil, however many we do sieve analysis on, is whether they're well graded or uniform, and if the percentages of those constituents correspond with the texture analysis we did way back in week 1, right? We're always going to be coming back to that soil texture triangle. And this is what, graphically your soil samples are going to look like based on those different gradation results. A well-graded sample here, you've got large particle sizes all the way down to your small particle sizes. And you see that graphically with a broad, not very steep curve. Whereas a poorly graded or a uniform sample, right? Every one of these soil particles is wearing the exact same uniform. They all look the exact same because they're the exact same size. You have a very narrow, steep, nearly vertical curve. So before we can graph results onto a distribution chart, we have to perform some measurements, right? A gradation analysis, and basically get some weights of particles after they've passed through a sieve stack. And we're going to take a half a dozen sieves and place them in a stack on try and hit the kind of those primary pan numbers, like your 4, your 10, your 40, and your 200 are kind of the key sieve numbers that separate out those major categories of particle sizes, like gravels from sand separate out the number 4, sands from fines separate out at the 200, and then within sands we have coarse, medium, and fine sand, and those things generally separate out at your 10 and I believe 40 sieve pan numbers. We'll look at that in a second. This is a picture of the results that we're going to see, or hopefully see this week. We've got some coarse soil samples, or coarse particles in a soil sample, less coarse, a little less coarse, all the way down to, looks like this might be our 200 sieve pan, and then we've got some stuff that even went through the number 200 down there, retained in our pan. So we're going to log these results on kind of this data sheet, and I've got copies of this also in your lab manual. And I just threw some numbers up here to run through a quick example calculation with you. Just to keep the numbers easy, I'm saying we're starting with 500 grams of a total original sample. And I'm not going to make up numbers for empty sieve weights and then sieve plus retain weights. What those refer to is you're going to weigh each of these pans empty, right? We're going to run our soil through the stack. We're going to agitate it here in this green shaker. You agitate it for about 5 minutes or less if you think it's a coarse soil. That's not going to take that long. But after you agitate it, then you carefully pull your pans apart and you need to weigh each pan again, right? And the weight of the sieve plus the retained soil minus the weight of the empty sieve that you started with is going to give you the number that we're ultimately concerned about here, the mass retained. What's the mass of the soil that's retained on each of your individual sieve pans? So I'm just giving us these numbers here to use for an example. We're not concerned with columns F or G this semester. Those relate to analysis we do on gravel for concrete next fall. All we're concerned about this semester is computing the results for column E here, and that's percent passing by mass. Another way of saying that is what's the percent smaller by mass than each of these individual pan sizes. So what we want to know is how much of our total soil sample is going through the number 4 and down on to the number 10 and below. And then how much was retained on 10 and went through on down to the 20 and below. And we do that individually. So what we should be seeing here are numbers decreasing in magnitude, right? Most of our soil sample is going to pass the larger opening. Less of it is going to pass the next largest opening. Less and less, all the way down to, hopefully, if we didn't make any measurement mistakes, 0% will be passing our pan. So just an example of how you run this calculation. I've kind of have an example calculation here up in the first couple rows in column E. In order to compute percent passing by mass, you take the total mass minus the mass that was retained on that pan or any pan above it. Right? And then you're going to divide that by your total mass. So, for example, we're on the number 4 sieve. We had 0% 90% mass retained on the number 4 sieve. That means all of it went through. All of our soil particle sizes are smaller than a number 4 sieve. So percent passing is 500 minus 0 divided by 500, which is 100%, right? Don't forget to multiply the results of this computation by 100 to put things in terms of a percentage. So we'd have 100% passing in our analysis sheet. Next pan was a number 10, and we had 50 grams retained on that number 10 sieve. So we're going to take our total mass, 500, minus now what was retained on the 10, 50, and everything that was retained above it, right? Because this is a accumulation thing. We need to account for the soil that was retained above it as well. So 500 minus 50 plus 0 divided by 500 gives us a 90% soil passing on through the number 10 sieve down below. So we'd have a 90 up here. And then we'll do one more together. And the number 20 sieve, right, our sieve pans are getting incrementally smaller. We had 75 grams retained on the number 20. We have to account for the 50 that was retained above it and anything that would have been retained on the number 4 above that. So our original sample, 500 grams, minus 75 plus 50 plus 0, all divided by our original sample, tells us 75% of our sample is passing on through the number 20 sieve down on below. So go ahead and pause this and work out the remainings here on your own. I have copies of this also on Moodle for you to print these off, and then I also have a blank gradation chart on Moodle that you should print off so that we can plot these results here. Okay, hopefully you took some time to pause and fill those out, and if you ran those calculations, these are the percentages you should have gotten. 40% passing the number 40, 15% passing the 100, and only 5% of our soil passing the number 200 sieve. And if you've done your numbers right, 0% should pass your pan. So if these are our results, we can take those now and plot them and start to develop a gradation curve for this particular soil. So what we want to do is take the sieve number, number 4, and the percent passing, 100, and plot that point on our chart. So here's our number 4 sieve line, this vertical line, and here's our percent passing, so 100 comes over here, and we're going to put a data point right there. We're going to do that for all of our available data points. So 90% passing the number 10 sieve. It's going to put us right there, and we're just going to do that for all of them. What I do on this particular graph is place a dot or place a data point at the very smallest diameter you have available and 0, because essentially 0.001 is a pan, right? That's too small to force any soil through in this dry sieve analysis. So even though this right here, this number 200, is our last actual measured data point, you can go ahead and just put a dot down there to represent 0% passing the pan. And what that allows us to do is place an interpolation line to kind of get a feel for what's happening with our finds. Once you have all your points charted like this, you can go ahead and connect them with the line, and then what this allows you to do is interpolate a percent passing on an important sieve number if you didn't happen to have that sieve in your stack. And what I mean by that here is, let's take a look at these important sieve sizes again. So this is a table we've looked at from the textbook a couple times. It's all of those important classification systems that we're working with. And USCS, right, the Unified Classification System, is kind of the main one that we're going to be working with this semester. And you can see they separate out, remember, along that number 4 sieve, your gravels from your sands, Down here at the 200, your sands from your fines. And then, according to USCS, at the number 10 sieve, they separate out coarse sand from medium sand, and at the 40 sieve, medium sand from fine sand. USCS does not differentiate between silts and clays. They call everything fines. So up here in these other two classification systems we've been using, AASHTO and the USDA, right, this is your soil texture triangle, they use this dimension right here, 0.002 millimeters, as the dimension that separates out a silt particle from a clay particle. So we can plot these demarcations over here on our graph and place a little line here that separates at the 4 your gravel from your sand, and a line here at 200 that separates your sands from your silts, and out here at the 0.002 millimeter, right down here is your millimeters, so 0.002 millimeters separates your silts from your clays. You can refine the resolution of your sands there at the number 10 and the number 40 as well. And now what we can do, that we have this gradation curve developed here, is we can use it to quantify and express the percentages of each one of these constituents in the soil. So what we would do first is we would take a vertical line and come down at the number 4, and then straight until it intersects our graph, and then straight over. And you can see obviously we're still at 0%. So that means we have 0% gravel, right? Because that number 4 is what represents the gravel. Well, next we'll come down at the number 10 sieve, and then straight over. And what this range here, the range between those two horizontal lines, represents the range between these two sieve sizes, because that's represented by this interpolation line on this graph. So that's made up of coarse sand, right, from a number 4 to a number 10 sieve, and we've gone from a 0 to a 10% on our scale, so we know we have 10% coarse sand. We'll come down here on our 40, come straight line vertical down until we hit our graph, horizontal line over, and we come out at the 60 line. So from 10 to 60, we know we have a 50% medium sand. Come down at your 200 till you hit your graph, or till you hit your line. Come over, and from 60 to 95, we know we have 35% of our soil sample made up of fine sand. And now here's where the interpolation line kind of helps you out on this fine here. We would come down at the 0.02 until we intersect our interpolation line, and then straight over, and you know, you can call it 1%, right? We're just above 0, which would tell me between these two horizontal lines, right, those two horizontal lines represent these two vertical sieve sizes. That represents silt. So I know between those two horizontal lines, I've got 4% silt, and below that I have room for 1% clay. Okay, so this type of analysis can become pretty handy when you're needing to identify the texture of your soil, right? And to go to something like the soil USDA soil classification triangle. The other important variable that we're going to try and deduce from our data here, our measurements, is the coefficient of uniformity. And it's an expression of the uniformity of the soil sample. And by uniformity, right, we just mean the particle size distribution. Essentially, we can look at that graphically if we've plotted it like we have, and we can see this is a pretty broad curve. It's not a steep, narrow curve, which would represent a uniform sample. It's a pretty broad curve. It's probably a well-graded or non-uniform soil. But there's these value ranges here that you could use to express that numerically. Whereas if your coefficient uniformity is equal to 1, you know you have a uniform soil. If your CU is between 2 and 4, you'd have what you call a medium graded soil. And if your CU is greater than 4, you have a well-graded soil. And Cu, your coefficient of uniformity, is calculated by D60 over D10, where D60 represents the grain size at which 60% of your soil sample passes. Or, in other words, when 60% of your soil sample is smaller. What particle size is your soil at which 60% of the original sample is smaller than that? And then D10 is the grain size at which 10% of the soil sample passes your sieves, or the grain size at which 10% is made up of smaller diameter particles. So the way you would come up with D60 and D10 off of your graph here is you've got percent passing, which represents percent smaller, and here's your 60 and here's your 10 line, and you can kind of see these lines are a little bolder than the rest. That's because they're used for this analysis. You come over horizontally along your 60% until you intersect your graph, and then come straight down vertically, and you're simply reading your particle size in millimeters off the scale there, and that's about 0.6 millimeters. This is a logarithmic scale, so each one of these lines represents generally one division. And so just be careful of that. Don't assume it's an equal scale between your lines. It is logarithmic. So you do the same for D10. Come over at D10 till you intersect your graph. Come vertical straight down, and you're reading about 0.11 millimeters diameter particle size. So to solve for Cu, it's simply 0.6 millimeters for 60% smaller divided by 0.11 millimeters for 10% smaller, or a numerical value of 5.5. Right? It's a coefficient number, so there's no units. It's simply a number used along this scale, and since we're greater than 4, we could call this a well-graded soil, just like we thought it was by looking at the gradation chart, or the gradation curve. So we're always going to be coming back, right, to this soil texture triangle, and we've just been kind of making up numbers just to learn how to use this triangle, but now you're starting to see where these values for percent clay, percent silt, and percent sand come from, and they come from these particle size analysis experiments. Now, if you looked at that gradation chart closely, you saw that the sieve numbers stopped here at the 200, and after that they had this little label here for hydrometer analysis, and this is a much better tool, or a much better test on fine soils to develop a particle size distribution. You really can't force small particles through pans much smaller than a 200. So this is the lab that we're going to be doing next week. To do this, we actually have to save some of the soil that passes through our smaller sieve sizes this week. So we need to make sure we remember to do that and not just throw everything back in the buckets when we're done with our sieves. But essentially the way a hydrometer works is you suspend your fines in a solution, and then you use a hydrometer, which is like a fishing bobber essentially, that has a scale on it, and you can read how the buoyancy or the density of your solution, or your slurry actually, is changing over time, right? Because you can see in this bottom picture, bigger particles fall out faster than smaller particles. So we're going to just essentially measure the height that our bobber or the hydrometer is floating in this water as its density changes by the particles settling out of it over time. We're going to try and do it for 2 hours if we have time. But that's really how you would fill out the I guess the tail end here, the fines portion of a gradation chart. not really with a mechanical sieve like we're doing this week.